So today we will move to grade 9 and we will uh, explain mechanical action, equilibrium, interaction, and Hooke's law. So consider a ball. If we drop this ball, it will fall downward, and if we have a table, the ball will fall on this table after a few seconds, so the ball will be on the table, and we can deform or change the shape of the ball if we exert a force on the ball. So these effects explain the existence of a force. For example, if we drop again a ball, it will fall on the second hand. So we can understand that some object exerts a force on the ball that makes it fall downward, which is the earth. So a force is nothing but a mechanical action exerted by one object over another object. So the earth exerts a force on the ball for the ball to fall downward. The object that exerts a force is called the actor, and the object that receives this ball is called the receiver. So the earth is the actor and the ball is the receiver. Each force has an effect. So why the ball did move downward? Because the earth attracted downward. So if the effects of forces are a force may let an object move, so the gravity of the earth let the ball move, so it causes this motion. Or maybe change the motion of the object. For example, this hand tries to change the motion of the ball, or may change the form of the object. So this hand change the form of the ball. So we have two type of forces. If the actor and receiver are in contact, then the force is a contact force, and if they are at a distance, then the force is a distance force. When the ball falls due to the force exerted by the gravity of the earth, then the actor, which is the earth, and the receiver, which is the ball, are at a distance. So this is the weight is a force at a distance. When a magnet attracts the iron, this force is at a distance because the magnet and the iron are at a distance. If you have two objects that have charges, they either attract each other if they have charges of different sign, or they may repel each other if they have charges of same sign. When we put a ball on a table, the table exerts a force on the ball, because if there is no table, the ball should fall downward. But since the ball did not fall downward, then this change of the motion is due to the force exerted by the table, which is upward, and this force is due to a contact, then this force is a contact force. We call this force a normal reaction exerted by the table. When we attach an object to a spring, the spring changes the motion of the object because it uh, because the object did not fall downward. And when we attach a ball to a string, the string tries to attract the ball. These forces are due to a contact, then they are contact forces. If we cut the string or the spring, or we take away the table, the object will move, and the change of the motion is due to a contact force. So in the previous slide we saw that the motion is either downward, upward, to the right or to the left. So the effect should be represented by a vector. A vector has a point of application where the force starts. So here the force starts at the contact point because the force is contact force, and here the force starts at the center of gravity because it's a force acting at a distance. The force has a line of action which is either horizontal or vertical, or this vector makes an angle alpha with the horizontal, or in some books we may see it as an oblique force. But we have infinity many oblique forces, so we have to be clear and say that it makes an angle alpha with a horizontal plane. And so the line of action is a line that holds this force. And the direction depends on the line of action. If the line of action is horizontal, then the direction is either to the right or to the left. So in this slide, the string tries to attract the ball to the left. Here, the negative charge is moving to the right. So the effect of the force exerted by this charge is to the right. If the line of action is vertical, then the force is either upward or downward. So the ball falls downward due to the weight, to its weight. Here, the table exerts a force and exerts an upward force on the ball. But if the vector makes an angle alpha, then we have four possibilities: upward to the right, upward to the left, downward to the left, or downward to the right. So depending on uh, how we drop the ball, the speed of the ball changes. So this is due to the intensity of the force exerted on the ball. So in this example, we will see the effect of uh, the forces exerted on the ball. We will assume the absence of the forces to understand its presence and its effect. So first we have to assume that we have no weight. If we have no weight, the ball should move upward. Why? Because the spring attracts the ball upward to the right, and the string attracts the ball to the left. Now, if we don't have or if we cut the spring, the ball should rotate to the left due to the two forces, the tension of the string and its weight. And if we cut the string, the ball should rotate to the right due to the two forces, its weight and the tension of the spring. So we can understand that we have three forces. Some forces change the motion of the ball, because if we don't have the tensions, or if we cut the string and the spring, the ball should move downward. So the tension changes the motion of the ball. So we have three forces. The first force is the tension of the string. We can see that the string attracts the ball horizontally to the left. So from A. So the force starts at the contact point A, and it's horizontal to the left, and we can't know the intensity of the force. We may measure it using a dynamometer. Another force is the tension of the spring. So the force starts at B, so the point of application is B, and the spring attracts uh, upward to the right the ball, and the line of action is a line making an angle alpha with the horizontal. For now, we can't measure the intensity of the spring, but we will later see how to measure it. And the third force, which exists for all objects having a mass m, we can see that we have the weight. In all cases, the weight is from the center of gravity G. It's vertical downward, and its intensity is measured using this formula, W equal m times G. So in the previous slides, we saw that each force has an effect, and if we have multiple forces uh, that of effects that sum up to zero, then the object is at equilibrium. What we mean by equilibrium is if the object is at rest, it should stay at rest, and if it's moving, its motion is uniform. What we mean by uniform, that the speed should not change, so it has a constant speed. And since we represent the effect by a vector, then the object is at equilibrium is the sum of all these factors, is a zero vector. So if we have an object that is subjected to multiple forces F1, F2, F3 to Fn, this object is at equilibrium if we have this vector relationship. The sum is a vector 0. So f1 vector plus f2 vector plus f3 vector plus fn vector is a 0 vector. So in grade 9, in multiple uh, in many exercises, we will see only two forces, and they ask about this relationship. So we'll write the relation of two forces only on grade 9. Now we will solve an exercise to understand how to work with equilibrium. Consider a ball that is attached to a string. The mass of the ball is 0.5 kilogram and take G equal 10 Newton per kilogram. Actually, G is not 10, it's 9.8. The maximum value is 9.81, blah blah blah. But we take it 10 for the sake of calculation and rounding. For the first question, we have to name the forces. And second, we have to indicate the type of the force, if it's a contact force or a force acting at a distance. And the third question, we have to indicate the line of action, if it's vertical, horizontal, or making an angle alpha, and the direction upward, downward, to the left, to the right, and so on. As the first question, we have to write the relationship between the vector forces, and finally we have to find the intensity of each force. We can see that since you have a string, then the string exerts a tension on the ball, because if we cut the string, the ball should move downward. So the change of motion is due to the tension of the string. And when the ball moves downward, so we have a weight on the ball exerted by the earth on the ball. So we have two forces, the weight of the ball W and the tension of the string T. T is a contact force, because if we cut the string so we don't have a contact, the force will vanish. And W is at a distance, because the earth is at a distance d from the ball. The line of action of W is vertical, because the ball will move downward vertically. So the direction is downward, and the line of action of T is vertical, because the string is vertical and the direction is upward. For the equilibrium, the ball is at equilibrium is the sum of all f vector is 0. So W vector plus T vector is a 0 vector. And finally, we can find W. W equal m times G using the formula. So 0.5 times 10 equal 5 Newton. For T, we can find T using this relationship. So T vector equal minus W vector, and the magnitude of each force is 5 Newton. For the representation, so W is vertically downward and T is vertically upward. Now we'll move to principle of interaction. From the previous exercise, so the tension exerts a force on the string exerts a tension on the ball, but also the ball attracts the string downward. It exerts a force on the string. So this is what we mean by interaction. If an object A exerts a force over an object B, then the object B exerts a force on A. These two forces have same line of action, opposite direction, and same intensity. So we have a vector relationship between these two forces. the sum of the vector forces is zero. So we can conclude that they have same line of action. They are collinear forces. They have opposite direction and they have the same intensity. In the previous exercise, the ball exerts on the string a force F such that F equal to T equal to 5 Newton. Now we'll move to Hooke's law. So now we'll work on the Hooke's law. So consider a spring of initial length L0. Now if we attach a ball to the spring will elongate and has a new length L, and we can see that the elongation is delta L and it should be equal L minus the initial length L0. So the forces acting on the ball are its weight, because if we cut the spring, the ball will move downward, and since the ball did not move, then the spring is attracting the ball upward. And at equilibrium, we have the vector relationship W plus T equal to 0, then T equal W equal M times G. We will do a simulation on the tension and the elongation delta L to find the formula of Hooke. So we consider different balls of different mass, and we find the tension using the equilibrium M times G. So for 0.1 times 10 it's 1, and for 0.2 we have 2 Newton, and so on. And we can measure the elongation delta L using a ruler. So we have measured it, and we will measure the ratio of T over delta L. For 0 actually it's indefinite, so for other values we have 1 over 0.01 it's 100, and for all the measurement the ratio is 100. So we can see that T over delta L is equal to constant K, so T equal K times delta L. And if we draw the graph of T in terms of delta L, we can see that the representation is a line passing through the origin. Hooke tried this experiment on different spring, and he concludes that K changes with respect to the spring, not with respect to the mass. So for the same spring, K is constant, but for different spring, if we change the spring, K changes unless the springs are identical. If two springs are identical, they have the same constant K. What is K? K is nothing but the spring stiffness, which means how the spring will elongate. So for 0.01 meter elongation, the force will increase by 1 Newton, so which is K times the elongation. But each spring has a limit elasticity. So if we exceeds a limit force Tmax, the spring loses its elasticity, and in this case we cannot apply Hooke's law. for Tmax, the spring can support a maximum mass and max. So if some mass exceeds this maximum mass, the spring loses its elasticity. And we know that at equilibrium we have Tmax equal Wmax, then K times delta L max, the maximum elongation equal the maximum mass times G. Thank you.